this section, we're talking velocity and acceleration. The goals are to calculate a position function's velocity and acceleration vectors. That's number one. Goal number two is to analyze projectile motion. Goal number three, to compute the tangential and normal scalar components of acceleration. And then we want to compute t, n, and b, whatever b is. What's the assumption? Generally, if I name an R of t that describes a curve C, generally we're going to think of it as being in space and having components x of t, y of t, z of t, although we could be in the plane at some point and it would just have components x of t and y of t in that case. So let's let R of t be a position function of an object that traces out a smooth path C. So what does that mean? Well, now that I said we're going to be in space, let me draw something in the plane because it's way easier. Okay, here's a curve. It could be in space, right? It could have some depth to it. You just can't see it. So here's a curve. Call it C, and it's given by R of t. Now, R of t, the parametric equations that make up the components of R of t, not unique, right? There are other parameterizations that could represent C. Always keep that in mind. So let's suppose that that's a curve C given by R of t. That's one parameterization for it. Then what do we mean by a position function? So let's say you have a particle or an object traveling along this curve. Then what R of t will give you, t would represent time, maybe in seconds, maybe in minutes, maybe in years, I don't know. And if this is an object on the curve and it's at the point given by R of t naught, then R of t naught, whatever point that is, it's gonna have components x of t naught, y of t naught, z of t naught, and those are actual, for any particular t naught value, those are actual constant values. And what this represents is the position of the particle, this point graphically, this guy symbolically represents the position of the particle at time t naught. Position, I'll say position of object, traveling along the curve, traveling along C at time t naught. That's what we mean by a position function. Does that make sense? And unless otherwise said, the position function is going to be nice and smooth. They're not going to have any sharp corners on it. So let's talk about some definitions. So the velocity vector, v of t, it should make sense that that's r prime of t. And in terms of the limit definition, it's the same as it was back in the second section. So it's the limit as h goes to 0 of r of t plus h minus r of t all over h. Assuming that limit exists and we have component functions that you can take derivatives of, then of course, component-wise, you could say that that's equal to x prime of t, y prime of t, and if there's a third component, z prime of t. So why does this definition make sense? Why does it make sense to call this the velocity vector? These components are calculus 1 type derivative, rates of change. In fact, you could even use Leibniz notation, dx dt, right? dy dt. And that reminds us of something, dz dt. That reminds us that x prime of t, dx dt, is the rate of change of the first component with respect to time, right? dy dt, y prime of t, dy dt is the rate of change of y with respect to t, the second component. dz dt is the rate of change of z with respect to t. And so it does turn out to be convenient to put those together in a vector, and it does give us some, as you'll see, meaningful information. So it is a definition, but there's a good reason behind it. It is going to offer us up some reasonable results, let's put it that way. So that's your velocity vector. Now your speed is actually the magnitude of that thing. So the speed is the magnitude of v of t, which is the same as saying the magnitude of r prime of t. And if you think back to that video on 13.3 that you watched, this should make perfect sense, because we have this result that the magnitude of r prime of t, remember, is ds dt. Oh, S is arc length. Oh, that's the rate of change of the arc length. That's the distance traveled along the curve with respect to t. That's a calculus 1 type derivative, isn't it? Yeah. So that's why we call the magnitude of v of t the speed. It's the rate of change of the distance traveled along the curve with respect to time. It's what you thought of as the first one interpretation of the first derivative back in calculus 1. The acceleration vector, you could guess at what this is. A of t, we call it? R double prime of t. Good guess, yeah. It's so you could think of it as v prime of t or r double prime of t. And component-wise, it represents, the first component is x double prime, second component is y double prime, third component is z double prime. It represents the rate of change of the respective components, which is how we defined scalar acceleration back in calculus 1. So it makes sense to put these values together in a vector. And as you'll see, it gives us something very meaningful. You won't see that till Thursday, but it does. And then we have something called the unit vector in the direction of motion, but it's something you already know about. It's the same as the unit tangent vector. Okay, it's just when we call it the unit vector in the direction of motion, then r of t is specifically a position vector valued function. So this thing is called t, and it's the same t we encountered at the end of last time. How do we find it? We take r prime and divide it by its magnitude, or in the language of this section. So I'll put both definitions down so you can see that it's the same thing we talked about in the past. It's r prime divided by the magnitude of r prime. That's got to be a unit vector, right? We described it as the unit tangent vector before, but now we're going to think of it as the unit vector in the direction of motion. Same thing in a more confined viewpoint. And then, of course, you could think of it as v of t, because v of t is r prime of t, divided by magnitude of v of t. So this is a vector that's 1 unit long. It will be tangent to the curve. It's the same as t of t. It's 1 unit long, and it points in the direction of motion. And it's tangent to the curve if you put its tail at whatever point you're looking at on the curve.